So hi, Frederick.
Hi, Lucio. How are you doing? You're muted.
No, because
It's okay.
unmuted.
Okay. Now there's echo. I did before, but they say they don't hear me.
We still cannot hear you. I see also Valeria is muted on Zoom.
Yeah, there we go. Now
okay, great.
Okay, we solved the problem. Okay. Okay, so I guess we can go back from the document. I see there are some more people than compared to yesterday. Especially we have the pleasure to have Frederic Massey here, who was kind enough to try join. I mean, Frederic and I have been in contact about code comparisons, including the KTP one. So I think it's great to have his input. So I'm sharing now the document that we wrote yesterday. Okay. So I guess I hope everybody sees that. Okay. So first of all, are there any comments by anyone about what we said and what we wrote yesterday as this tentative plan? Any new inputs? So I don't know, Frederic, if you had time to look into that. It's a very schematic thing.
Yes, I did have a look at it, and I have, unless I did not understand something, it very much looks like a planet in a disk, no?
It is, yes.
Except for the viscosity, which is much higher.
That's right. Yeah, exactly. Viscosity,
okay.
because we have in mind the accretion disk of a black hole.
Yeah, okay, okay.
The other difference in principle, but we were discussing that yesterday, is also the H over R for the same reason, because you expect a thinner disk. But we were debating that maybe from the beginning, it's better to start with something more, let's say, standard, like 0.1, because some codes might have more trouble in going directly with the very thin disk.
Okay.
I don't know if you have any input on that. So because in principle, H over R 0.01 would be preferable for this application, but it's quite thin, and for some codes it might be not so easy numerically to do.
I think it needs to be tested, but that's quite different from the planet's standard setup, because we will have, with such a small H over R, you would open a gap, but with such a high viscosity, you tend to close it. This is very much way off what we have usually with planets, like Jupiter mass planet in this.
That's right. Yeah. So we were saying maybe we start with 0.1 because there's more literature around, and then we might reduce it later.
Yeah.
Yes, and then the mass ratio is 10. We decided maybe 10 to the minus 4 might be the starting point. But even that, I mean, we might go to higher later. And then the idea was to start isothermal and adiabatic, so local isothermal and adiabatic. then again, we can upgrade this later with some cooling, but for the beginning, it's easy to do it in a clean way like this. I guess you probably agree. And then, what else we can discuss? Let's say, I don't know if there are other things that people thought about in the meantime. So one thing that we were discussing was also the boundary conditions, because especially for the grid codes, there are different defaults, and maybe Frederic, you have some comment on that. For example, for Fargo, I guess you have different ways of doing boundaries, and you probably have a default that you use for this type of setup.
Yes. Do you have the boundary conditions here in this document?
No, we were discussing. We haven't actually said that yet.
Okay. Well, so I'm not sure. Something that will happen with a large viscosity is that there will be a fast drift inwards of the disk, and the boundary conditions need to accommodate for the inflow. Now, with the H/R you want to try first, and the small secondary to primary mass ratio, you won't get a very strong wake. So I think any kind of boundary condition will do the trick. You might not even need wave killing boundary conditions, which damp the flow towards the boundary conditions.
Yeah.
Which needs to be tested.
Yeah. Yeah, because of course, in the list of codes that we preliminarily compiled, there are some that can do with no boundary, like the particle ones, the SPH and MFN. Then there are of course codes like Fargo and Ramses we put, and Athena, and also Disco. So each of them is likely has a different implementation. For Disco, I think for Disco you Andrea, you can correct me. You use the inflow boundary condition.
Yeah, or you can have a fixed boundary condition. Depending on what you want. Those are the only two I've experienced.
Mm-hmm.
I guess in principle you could define any one.
Mm-hmm. Yeah, I mean, I guess the idea would be to start with something that every code, the particle ones don't need a boundary condition, but the other ones will need one. And if we have one that is basically the same across all of them, it would be ideal.
I have a question on this document. You say that in a second stage you will repeat your simulations with sync particles. So you mean you will have accretion onto the secondary?
Yes. So this is, I mean, certainly will not be the first part of the project, but eventually there are reasons to do it because, well, accretion is an obvious thing to model for black holes.
Yeah.
And I mean, you know better than me that when people do it in the context of planets or protostars, they don't find easily convergent results. Actually, it usually becomes a mess.
Okay. So you want to check the talks without a sync particle and with a sync particle to see how accretion affects migration. Okay.
Yeah. Exactly.
Okay.
Because I mean, the sync, in my experience, can introduce a lot of numerical effects, and they will be different for each code. And I think it's very interesting to see what comes out of the comparison. But first, we should have a good comparison without it. We should hope to converge decently without it, without the syncs.
Okay.
Which is also not obvious. As you said, it's a slightly different regime from what people have done in the past. And then there is also this aspect of the torque fluctuations, right? I guess David has talked to you about that probably. Because David and Andrea had started comparing Disco and Fargo, looking at the different amount of fluctuations of the torques around the secondary black hole. And I think it's a complicated business.
Yes. I mean, basically, we don't see those in Fargo 3D, but that was for the set of simulations, one small set that we ran.
Yeah, so this would be another question, at least in this community is very relevant. So first of all, are there significant torque fluctuations in all the codes? These are usually seen near the secondary.
Yeah,
right? So
close to the secondary.
just close to the secondary, or creating this fluctuation. So sort of E-radius scale.
Yes.
And it's relevant because it has effects that might have an impact on the gravitational wave in spiral. So it's really good to know if there is some additional drag due to these fluctuations of the torques.
I guess that would be the second thing to look at, though, right? The first thing is just look at
The
compare average
mean
torques.
migration rate, if you want.
Yeah.
The mean torques, and therefore the mean migration rate.
And then looking at them, but like not smoothed, just the raw torque data from the simulation could be interesting to compare.
Not smooth, I mean, just
Sometimes there's
without
some-
doing any smoothing.
Yes, like over time.
Yeah. So in the analysis, we should say that that's, initial comparison. Now, the other thing is we are, of course, trying to identify code captains, so people who can be responsible for each code. We wrote down some names of people who volunteered or potentially are going to do that. And I mean, for Fargo, I took the liberty to put down David and you, but just because we talked about that in the past. But I mean, if you have in mind other people who might be interested in running Fargo in this context, just let us know.
Okay.
Because I don't know, I don't know if David has time now to do that. Yeah, we can check.
I have a question about the live binary simulations, if that's relevant.
Yeah, go ahead.
For those, you need to choose a disk mass. So
That
what
is correct.
Is there some, would we choose some type of value based on a inner AGN accretion disk model, or what's is there something being done with the KITP one, or there's no live simulations there, so there's no comparison?
So what I personally did was to assume a finite mass of the disk, and then, fix the binary orbit. And when I do the comparison, like when I calculate the various quantities, then I rescale my particles mass to the one that people have in grid codes.
But so in the end, you have the same mass ratio, I guess, between the disk and the part. I mean, that what really matters is also that, right? The mass ratio between the disk and the particle.
The disk and the particle.
So should it?
So
because yeah.
I'm not sure honestly how this works in Disco, for instance, as you have the m dot, which is fixed at the outer binary. So yeah, of course, in particle codes, you fix the mass of the disk, which is like 0.1, the mass of the binary. And then each particle will have a mass 0.1 divided by the number of particles. So that's straightforward. But essentially, what we cannot have if we use the profile of sigma that we agreed upon for the code comparison, the KITP, as it is, with sigma 0 equal 1, far from the binary, then that is not feasible in SPH, because then that means that you will have the disk which is way more massive than the binary. And so that doesn't make sense.
Wait, I'm confused.
Yeah, I don't.
Can you not run the, I don't do SPH simulations. Can you not run it in the limit of 0 mass with the particles?
No.
No.
You can in principle assume a very, 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 very low mass disk.
Yeah.
That you can do, like 10 to the minus 6, the mass of the binary or something, or even 10 to the minus 8 if you like. But that's about it.
Yeah, because otherwise you have no density and you cannot integrate the efficiency.
Okay, and then that would have to be the case for the non-live.
Yes, for the non-live you have to assume a very, is it what you're doing now, right, Alessia? You assume a very low mass.
No, what I'm doing is actually fixing the binary orbit in the code. So like not updating the sync particles, the sync properties. But then the other way to do that, which is what Enrico is doing with Phantom, is simply to just decrease the disk mass. And to, I don't know, I think he uses like 10 to the minus 6, the mass of the binary. And that essentially fixes your binary orbit.
Yes. Yeah. Yeah, I mean, these are things that, of course, there's different implementations you cannot completely remove, but usually, I mean, with that slow mass, it should work.
Yes, it does seem to work. So,
but it's still not clear to me in the live case then the mass of the disk. In the case of disco, for example, you would set
arbitrary. I mean, so
if
someone said it has to be 1, then it doesn't mean anything. It just means that it drops out of the equations. It doesn't matter what sigma is. If you're not updating the orbit of the binary, once you're updating, you need to choose a physically limited value.
You can do it. I mean, it's already possible. Yeah. Right. And
but I guess I was just wondering
what you should
do. Choice for that, or maybe just address it when we get there. Or?
Yes, I mean we have to address it at some point, but maybe not for now. But we have to have a model in mind. Yeah, because in the case, for example, the protoplanetary disk case, there are some standard models that people use, even for the mass. There is this minimum sort of mass nebula. There is a very well-known mass scale, and then that's what people assume. Either they put it, explicitly, or it's implicitly interpreted like that when you do the analysis.
Yeah.
If it's scale-free, for example, then you rescale for that mass. But in our case, you're right. I mean, we don't have a default mass.
You just have to choose like a fiducial system, right? If you set the mass of the primary to something and use an alpha disk model, you get disk density at some accretion rate.
Yeah.
So I guess
maybe using density or accretion rate as a proxy.
Yeah.
So we have to we put a note about this. Okay, put it next to the line. With the profit, of course. That is said before, so that's okay. Yeah. Okay. Any other comment or unclear thing in the sketch that we have?
Just a question. The pressure in these disks, is it dominated by the gas pressure, or is it by the radiation pressure?
Yeah. That's a good question. Well, it depends on the place in the disk where you're modeling the system. But so if you go very, in the inner part of the disk, you're dominated by radiation pressure. But I guess we can interpret this as more like the outer part of the disk.
It does, it also depends on what is our fiducial system, right? Because you can scale it.
Yeah.
So I think it's maybe nice to point out, what is our
Yes.
target?
Yes, that's
You
a
know, like
good
a
point.
Lisa type binary,
It's a good point.
separation that would imply.
Yes, that's a good point. Let's say decide. Yes, I mean, of course, at the level of using just an adiabatic equation of state, we could simply play with gamma to make one or the other case.
Yeah.
But we have to decide, of course, you're right. Yeah, that's a good
Actually, I
point.
don't know
for
if
the-
there's simulations that do that actually, radiation pressure dominated.
I don't know, actually.
There must be, no?
Yes, but I mean, not in this context.
Yeah.
I mean, there are the complex ones with gamma MHD and all this, or MHD and radiation. But I don't know, maybe Frederick, you know, have people ever done a setup like this, but using just an adiabatic equation of state, but just a gamma 4/3? So like you expect for radiation pressure.
I don't know, maybe, but I would not be aware of it.
Yeah, I have never seen it, but I mean, incidentally, that's a value that people who do protosterity sometimes have used for a different reason. You can use an effective gamma, see that not far from that, for other reason, for molecular dissociation when you're close to the core formation. But I don't think in the disk case, no. Anyway, I now decide reference scenario. So, okay. Pressure. Just this accordingly. It is true that in the circumbinary disk simulations, also in the KTP code comparison, the assumption, unless you know better, I mean, the assumption is you have an adiabatic with what? With gamma 5/3 or 7 feet. I mean, that, assuming thermal pressure, right?
We don't do adiabatic.
But you do isothermal, right? You do only.
We do isothermal, so gamma is equal 1, and yeah.
But you didn't have a plan also to do adiabatic originally? Or?
I don't think so.
Okay. Yes, so the isothermal case, it's more trivial because we don't have to decide anything. We just put the isothermal equation of state.
Mm-hmm.
Although, I mean, yes, yeah, we decide the temperature based on HRR and that's it, basically.
Yes, exactly.
Timescale wise, do you think that how many of these runs should be done for one publication?
Yeah, that's a good question. I think it's hard to say now. I think it depends a lot on how easy it is to get convergence in the first step. You know, let's say we start with isothermal, fixed orbit, so really stripped down to the minimums, fixed orbit, circular, isothermal, no sink. And then we already have some issue with convergence. Then we have to check many more things. And maybe in the end, the first paper will go only up to the live and have no sinks, maybe. If we have already a lot of trouble with converging without sinks.
The idea is to distinguish why there's a difference.
Yes.
Ideally.
Well, first of all, how big is the difference? Because I guess we need to know how well the orbital decay rate is understood in simulations. And then, yes, and then the reason of the difference. If the codes are not aligned naturally, can we align them? And in order to do that, we need to understand what's the reason. And then we have to do a lot of tests. So it's, I mean, at the very beginning, it's hard to say in these code comparisons how long it takes to do some stuff. And I mean, if you spend a lot of time already in the first stage, maybe it's forced to publish just that.
Is there like ever an issue of, say just for simplicity, two codes start to diverge or have different answers and you don't know which one is correct, right? So
You don't, yeah.
Is there sometimes some pressure for like one code to converge to the other, or is it like you need to see why maybe both are wrong?
Yes,
or-
I mean, the approach, I mean, sometimes people are biased inevitably by their own code, or their own, but the approach should be, we have to be completely open. No code is better than any other code, in principle, in reality too. So, I mean, if we get to a point where, I mean, there are sometimes funny things, you know, in this code comparison that we did for the self-gravitating disk with the, so this is the Fletcher et al. Paper, Frederick, I don't know if you saw it, with the massive planet or brown dwarf in a self-gravitating gas disk. So there was a funny result. At some point we had, in a few of the plots, you can see that there are some SPH codes that are more different between each other than, say, one SPH code and Fargo. So, and this is not completely clear why, but the difference is stronger when you add the sync. So with the sync, the implementation of the sync can scramble the results around, even if the methods are more similar, they should give you more similar results. You can scramble them around, and the Greek code is similar to an SPH code, and SPH code becomes more different from the other SPH codes. So it can happen like, but yeah, I think, you know, we have to be as objective as possible, and we really think about the convergence of the group of codes, and not specifically one code versus the other. Yeah.
That's a frequent situation that codes disagree on benchmark projects, and we don't know which of the results is the right one.
Yeah.
Now I would tend to think that this happens more frequently in low viscosity disks, and here we have such a large viscosity that it should smooth out most of the differences between the different codes output.
No, you have a good point. Yeah, we might be lucky from the beginning because of that. That's right. Yeah, it should at least help. Yeah, that's true. Yeah, actually, concerning the viscosity, yes. So I mean, there are codes that don't have an explicit viscosity. I mean, it's none of the codes that have already a code captain actually, but yeah, for example, the Ramses, or I don't know about Pluto, but Ramses, for example, it doesn't have an explicit viscosity as far as I know. So we have probably to be introduced. But I think, you know, for the SPH codes and for Gizmo, of course, it's not an issue, because in SPH is necessary to put it, so it's not an option. And so for Disco you have it, and Fargo has it. Yeah, so a good number of code has some way to do viscosity from the start. Okay. Okay, so then there will be, of course, the choice of resolution. So we didn't actually decide what resolution we should start from. This is something that we were planning on discussing once we have clearly each code with a code captain, or even more than one. Then we will have a Zoom call, hopefully before the end of the summer, where we add all the things that are still missing here. You know, we really decide everything about the initial setup, including the resolution of the first set of runs, and the softening, which, you know, it's also something that is not implemented exactly the same in all the different codes. So we have to be careful there too. So I guess the timeline could be that by September we have this Zoom call, and in the meantime I take responsibility for chasing down people and making sure that really there is at least one person responsible for each of the codes.
Out of curiosity, how many codes are you going to
So we
benchmark?
put, so the list that we have now as 1, 2, 3, 4, 5, 6, 7, 8, 7 to 8 ideally, and for 5 we have already people who are kind of agreeing to do something, and then maybe we'll add more. I put down also a repo which is like it's a moving mesh code. I will contact Deborah to see if she's interested. Yeah. I think that this other code comparison KTP, which is on the circumbinary disk, so it's more equal mass binaries than what we want to do here. They have also, you said it yesterday, Alexa, do you have 7 or 9 codes in the
Do have 9.
9? Yeah, so it's a similar size. I think it's a normal size of participating codes. Yeah. And then we were talking about doing uniform analysis also, try to maybe possibly use the same tool to do the analysis. We were talking about examples like YT that you know, can read most formats from most particle and grid codes, or maybe HDF5. Most codes have HDF5 interfaces, and YT is one tool that can do all of this. But you know, maybe in this not Zoom for the final definition, someone will have another proposal for an efficient tool to use throughout. But I would say YT is a possibility to keep in mind.
Well, it depends what we're looking at, right?
Yes, it also depends, yeah, you're right, depends also on what things have been implemented already for the type analysis that we want to do. In fact, YT does a lot of stuff, but the torque analysis itself, yeah, we were saying yesterday, maybe it's not directly implemented.
Yeah, I feel like it might be better to do it
Just a Python
like brute
script.
force.
Python script.
Yeah, exactly. Yeah.
Yeah. I mean, that's fine too. Let me re-emphasize it here. Okay.
It just depends maybe on what coordinates
Yeah.
your data is in and stuff like that.
Have you decided for how many orbits you want to run the simulations?
Good question.
Good. Yeah, we haven't actually. Yeah, so.
Depends on the viscosity.
So in the work that has been published, that is similar to this, like your work, Andrea. How long did you run the simulations?
At least a few thousand orbits.
Okay, let's put it just as a reference.
Yeah. Like one thing I've seen is, for example, if your boundary is too close, then you would have this like long-lived transient. But yet you still need to run for at least more than a viscous time at the position of the secondary.
Yeah. At the initial position.
Yeah, I was in stationary.
Yeah. Okay, let's say of order a few thousand.
Is there is it just assumed that everyone has their own resources for computation?
Tricky point. So I was hoping that in the first, at least for the first set of runs, the easy ones with no sync and so on, we should be also faster, right, to run with the fixed secondary, that people would do it on their own local resources. Then if the code comparison continues and we realize that it's a bit too much for some participants, we can think of solutions like where we, for example, in Zurich, we do have usually quite some computing time. So we can definitely think of helping if it's needed. There will be other places, not just Zurich, that maybe have more computing time than that mean. And so they should maybe ready to help a bit in that sense. Yeah, with Agora, for example, we had this problem a lot because they are expensive simulations, cosmological simulations. At some point, we actually got a special allocation for the code comparison. This was like in the early stages. Then it became more like we help each other, depending on who has more time at a given point in time. Yeah. Yes, but it's a good thing to keep in mind that we need to make sure that it's sustainable, basically. But I think the first set of runs should be quite easy to carry out.
Yeah.
Computing wise.
Yeah.
Let's see. Let's put down a note here. versus- Yeah,
I have another thought at the top of the document is about the order of projects.
yeah,
'Cause it's like multiple.
yeah.
I guess I feel like there's some, freedom in the order in which we change things. So for
Mhm.
example, imagine that we run, I see a question in the chat, I get to in a second.
Okay.
If we run isothermal, fixed orbit, et cetera, and there's well enough convergence and we move on, then you could move on to adiabatic, or you could increase Q, or you could reduce H over R. And is the plan to do, to set,
What's the
an
set
order?
priority, you mean?
Yeah,
Set of
exactly.
priorities.
Because I don't think it should turn into a huge parameter
No.
study comparison. That will take way too
No,
long. I think there should be a
absolutely.
clear set of priorities.
Yes, we should, no, I agree. I mean, all these things that we wrote are interesting to do, but yes, we have to have a priority list. So what could be, I mean, if the first phase goes fine, so going to lower H over R is interesting. But again, we might have some codes that have more issues than others to do it. So maybe the thing that is less numerically demanding that we could change immediately would be the mass ratio, I would say.
Yeah.
Right? Maybe that's kind of obvious.
Yeah,
Or you had
to get
something.
more to the IMRI
Yeah.
regime.
Yes, exactly. Exactly.
Then I would vote changing the aspect ratio, but I think it just depends on what you're interested in particular. Like before adding a sink, for example,
Mm-hmm.
because especially if you have 0.1, right, it's quite
So
thick,
quick.
right? So I don't know, the distribution of gas close to the black hole will be kind of smooth. I don't know how.
It might be not so relevant in the end.
Yeah, but then once you start to decrease the aspect ratio, you have.
Okay, so let's say that we will try to find out whether all the codes should at least be able to run H over R 0.05 without too much problem.
Yeah.
Which is, yeah. Okay, HR.
I see a question from Saida in the chat.
Yeah.
Asking if these runs are for black holes embedded in disk. The answer is yes. Well, that's the inspiration.
Yeah.
Although it's not, I mean, they're smooth point mass potentials. So if you want to call it a black hole.
Yeah. Yeah.
Okay, thank you. I missed the beginning part of the conversation, so I just wasn't quite sure.
Sure.
Yeah. Yeah, the idea is to model something that would be interesting in the LISA band or for a LISA type black hole binary.
Yeah, one of the things that my simulation looks at is actually for not embedded, like for inclined black holes in interacting with the AGN disk. And we were also interested in considering them as potential candidates for LISA detectable IMRIs and EMRIs, because we find for initially prograde inclinations for these 10 or 50 solar mass SBH, when they're being embedded in the disk due to the drag forces in the process, they migrate to like the innermost regions of the disk. They don't go all the way to the inner limits of the disk, but they tend to hang out around 10 to the 1 or 2 or 10 to the 2 or 3 RG, depending on the disk type. But one of the issues that we have as far as being able to say anything about LISA detectability is it doesn't go as far in as we would like, but even if it does, even for the cases where they do go in to like the 10 RGs or something, we don't account for general, like for relative, like for GR effects appropriately at those distances. But also the trouble tends to be, as far as disk models, what do you do if the disk models don't go that far inward?
This is all, I mean, we will all do Newtonian here.
I guess, I mean, we have like some solutions for accretion disk models in the inner regions, you know, around tensor radii that could inspire the parameters of the simulation that we're choosing. But of course, it's not going to be, won't be as realistic. Yeah, there won't also be an all Newtonian simple density temperature profile. But it would still, I think, be interesting for, you know, if you wanted to estimate the subsequent migration of those black holes once they are embedded, at least the prograde ones. We are also focusing on prograde. I guess that's another.
Yes, so we didn't say that explicitly, but yes, maybe we can say circular prograde just to make sure.
And we're assuming embedded, like zero inclination.
Yeah. We're also looking at circular orbits because from previous studies, we find that things get circularized, orbits get circularized before their inclinations decay. So a lot of things are captured in relatively circular orientations.
That actually reminds me of another point I had. I mean, there's a million things we could compare in simulations, but I feel like in the IMRI case, there are situations where you could have eccentricity pumping.
Yeah.
Seen in some protoplanetary disk simulations. It could be cool to measure E dot, like they're doing for the circumbinary disk simulations. But I think that's also something that would go lower on the list. I think.
Yes, I mean, I think it's very interesting, but I think it goes more into the direction of actual science project. I mean, It's more like if we know that we can converge well on the basic numerical setup, then we can look at more interesting stuff like eccentricity. I mean, this is the way I would approach it.
I want to do personally.
But I agree. But I mean, at the level of the code comparison.
That makes sense, actually, if the solutions are already converged and you don't need to calculate every.
So if things go well, maybe we can add these kind of things already in the code comparison. Let's put it like somewhere.
It's in my own.
You put, okay.
Oh, yeah.
As far as eccentricity pumping, one paper does come to mind, although I believe it's for retrograde embedded SBH in accretion disks. I believe it might be Secunda 2020, but I can find a link if you guys are interested in looking at existing studies.
Sure.
Yeah, this was a highly eccentric retrograde memories, I think.
Okay.
I think the takeaway from that paper was something along the lines of if there's if it's not like exactly circular, if there's some eccentricity to begin with, and it's embedded in retrograde, then you see like really drastic eccentricity pumping because.
Okay. Yeah, no, I mean, from the science point of view, it's very interesting. So.
You're right. This isn't as much a science project as it is a code comparison.
Yeah, it's functional to science.
I need a reminder.
Yeah. But it's important because then one is more confident to do other things like eccentricity or
Exactly. I see.
So you mentioned the possibility of retrograde orbits. This is something we hardly talk about for planets in disks, but maybe for black holes in AGN disks that may happen.
Yes, so there are, well, you can see something.
Yes. Oh yeah, so you're sending a link that has to do with this, but I mean, if you had black holes that were captured in the disk, captured meaning they intersect the disk and their inclination changes, you could potentially capture retrograde orbiters. So there are reasons to expect.
Because, sorry, the problem with retrograde is that they are faster. I mean, they have a higher in frequency, orbital frequency, no? Is the problem?
You mean, why are they captured, or, I mean, you could also capture prograde. Saida should answer this because this is her expertise more than mine.
I didn't catch the question.
Why, go ahead.
Okay, no, I mean, I don't understand. I mean, I understand there is a sort of a problem between prograde and retrograde, and the retrograde seems more problematic, but it's not clear to me, which I'm not an expert on this, why. So I was wondering if you can comment a bit more on this.
Are we saying, when we say capture, are we saying captured by the central SMBH?
I meant captured by the disk.
Ah,
meaning it goes to
so
zero.
So okay, so if we're looking at inclined retrograde orbiters being captured by the disk, in my particular simulations, we look at initially circular, and we're looking at things that are captured in circular, as circular orbits in retrograde orientation. They take longer actually than prograde to be captured, because like so the same inclination, say in retrograde versus prograde orientation, it will take longer to be captured in retrograde because it's not it doesn't migrate as much as the initially prograde orientation. So we find that for SBH, the more prograde you are, the higher the change in the radius, and the more that migration is, the faster it's captured by the disk, if that makes sense. So like once things start getting captured in retrograde orientation, so when they stop flipping into prograde, then the time scales for being captured by the disk are a little bit higher. Still within lifetime in some cases, but if you're just directly comparing to like the retrograde versus prograde counterparts of the same inclinations, the prograde get captured faster and closer to the central SMBH, if that makes sense. I don't know if that answers the question.
When you say capture, you mean that you really, because I mean, if it crosses the disk more than, so it takes a fewer orbits to end up in the midplane of the disk. Is that what you define capture?
Yes, but more than a few. Depending on the simulation, it can be anywhere from a few hundred passes through the disk to many millions of passes through the disk. So like that's also like why we consider like ranges of AGN lifetime to sort of also differentiate between things that are captured like in a like realistically feasible timeline. Yeah, I don't know if that's a explanation.
So the difference in the retrograde versus prograde is this, basically, that they need more, the retrograde need more orbits to get in the midplane, basically. Is that, I mean, I understand it correctly, or?
They need more time, but less orbits. And the reason for that is because the further inwards they move, the higher their orbital frequency. So the more passes they will need through the disk, but also the less time they will need in the disk, because the further inward you move, the denser the disk density tends to be, at least for the models that we're looking at for SG. So Circle and Goodman or Thomson, Porter and Murray type disk. Generally, the further inwards you go, the higher the disk density. So the more the black hole migrates, it'll have more passes, but less time. Sorry.
I'm sorry, is there a reference for this? I'm completely ignorant about this, so.
So I'm referencing right now a paper that's in prep, but there is an existing paper that's already published that has like some like preliminary results on this, but it only includes the prograde case. So the paper that will include retrograde results as well as higher mass SBH, that's something that it's in preparation now. It's actually honestly done now. It's in the final stages of like proofreading and such before we post it on the archive. So hopefully in the next few weeks it'll be there, and I can also email people if you guys are interested.
Okay,
Thanks.
thanks. Yeah. Okay, so any other points? Stage?
That's initial conditions, things to change in which order. Yeah, I guess that was my main question earlier, was just like, are these separate projects, or is there a clear indication of when it will be?
When the project is done. I mean.
Yeah, but maybe that's too soon to ask that kind of thing. I just want, like, I think.
Yeah, I really think that, again, if the convergence is not coming out easily, maybe it will, because the high viscosity, as Frederick is saying, maybe is helping us. But if it doesn't, maybe we could even stop before the sinks and already have something to publish before the sinks.
Yeah.
If instead the first part goes very fast and we get convergence easily, then we go to the sync part, and then it will take time, because the sinks are always calling trouble. But then we'll have to do more stuff to get the paper out. Yeah. Yeah, so it could be either we stop at 2 with the live secondary, let's say. I would go at least to the live secondary. Yeah, this is my opinion, but maybe it's not necessarily the opinion of everyone, but I would like to get to the first paper that we have already looked at the live secondary. Let's say maybe minimum.
Is there a format to submit the results?
What do you say, Frederick?
Have you decided about the format to submit the results, or is it free?
You mean that for the analysis?
I don't know. Is there someone in charge of gathering all the results and?
Yes, no, you're right. So yeah. So this is an important. So we don't have all the code captains yet. So I have to again chase down a few other people and have, I have a clear list of committed code captains for each of the codes. And once we have that, we really need to do what you said. I mean, we have to have this Zoom call by the end of the summer, where we define the things that remain to be defined, including someone who has to gather the analysis. Call it the general captain, of the. Yes, that's
all right.
You put that. Absolutely, yes. Also, the KTP one, they're doing it. I think Paul, right, is the one who's gathering all the Paul Daphne.
I'm not sure.
Yeah. Okay, let's put it from the top here. Yes. Here, right now. Okay. Let's call it analysis captain.
Hi. Can I say something?
Yeah, that's fine.
Hi. So I just note that. Hi. So this, in addition to the KITP one, is biased strongly towards 2D viscous hydrodynamics. There are 3D SPH codes that are involved, but they too are viscous hydrodynamics. I envision that in the future, we could compare things to 3D MHD codes. I think this is it's a little too bad that more people don't use MHD in this science problem. So I just wanted to I guess alert people that many people that are familiar with angular momentum transport in accretion disks recognize that viscous hydrodynamics doesn't adequately describe angular momentum transport. In particular, the thermodynamics and the electromagnetic emission from these disks. So, and it's not clear how these internal stresses affect migration of the secondary black hole. So even for the sake of just the gravitational waveform, it's not clear. So I just want to include this in this write-up. It seems like it's following in the footsteps of the KITP one that also is not looking at MHD yet, but the KITP discussion did recognize this issue, and that the first project was to just do something that could be used as a first step towards a comparison with a problem that like a lot of people could do. So I just want to send that message to you all.
I think you're completely right. I mean, it's true. I mean, we are doing something that we know is very approximate to the limit of being wrong in this regime, but I think, yeah, I would take the same approach that we start like this because it's something that many codes can do. And we want to be able to see that even in this relatively idealized case, we get convergence. But I mean, I agree. I mean, we could imagine that in the future we do a second code comparison with MHD among a subset of the codes. I mean, I would definitely like that. I mean, I'm definitely interested. I think many people are interested in looking at this regime for the binary decay. I mean, looking at the binary decay with MHD. You're right that it's a big missing part of the physics. Yeah. Yeah. So I guess we can put a reminder that the long run.
There's a lot of ways where we're not simulating realistic systems. So I don't know. I guess we just have to do one step at a time.
Yeah, it is true that the MHD also for me it's probably the most worrisome non-included thing is most of the work that many of us have been doing because, well, actually, I mean, Frederic remembers from the papers of Richard Nelson many years ago in the low mass planet case where, he was one of the first people in that field at least to highlight that you could have stochastic torques when you had included MHD. And so it was clearly different from the usual type 1 migration. So, I mean, that has to be
yes,
I don't know.
definitely.
Yeah. Yeah, that's okay. And here, of course, we have,
I just wanted to so you have these code captains. I just don't want to lose touch with this project because we may not be involved in this, early comparison.
But maybe the second, an update with MHD. You're thinking that might
there are other people that are. I mean, I know. Bruno Chikamatsu has done binary evolution. There's the Illinois group that does binary evolution with GRMHD codes. So there it's not just our group, but so and also Athena has the ability to do MHD, but I don't know who's using it these days for this problem.
So you would, I mean, thinking again in long term, if we do a second version with MHD, that would still be, I guess, not GR because that becomes that becomes a different set of codes probably. Most of these codes will not be.
We would have to think of. I think it's not obvious, right? It's not obvious to me what would be a fair setting for this comparison between Newtonian, viscous codes and MHD codes. Like our setup, we can certainly separate the binary into the Newtonian regime, but then the dynamic range and time scales and spatial scales makes it challenging because if you don't excise the black hole. So right now we are looking at the circumbinary disk in the Newtonian regime to see if there's any effect on separation, at least for the sake of the circumbinary disk dynamics. So, so maybe something like that could be done with different codes.
That's a very interesting point. Yeah.
I think it'd be really interesting if I mean, I guess it's not as clean of a code comparison to just throw in an MHD simulation for this first part of the project, but even if you had a simulation of similar parameters,
With MHD.
just to compare, I mean, how different are the results?
Yeah.
I think that would be really
Yeah.
cool to see.
Yeah. So using the same parameters, but
Yeah.
instead of viscosity, you do MHD.
Yeah, so then maybe you have to find a way to calibrate it, and I don't have any expertise there, I don't know how difficult that
Yeah.
is, but if you could have an effective alpha that was similar.
Yeah.
Yeah, that would be cool to see.
Yeah, no, that's true. I mean, if this one proceeds fast, maybe we can have these upgrades sooner than we think, but yeah.
Then this may branch into more than one simultaneous
Yeah.
code comparison.
No, and also, no, it's also true that, as we were saying yesterday about the general idea of these projects inside the LISA consortium, that there can also be smaller projects that people start spontaneously, even inspired by one of these more big collaborative projects. There might be some subset of people who decide, okay, we do a smaller set of simulations with MHD using just a subset of codes. I mean, it's open-ended in a way, right? It's not like,
There has been a few attempts in the planet disk interaction field to replace the traditional picture of an alpha disk with proper MHD simulations, in which the disk would be subjected to MRI. It's a completely different field. It's extremely computationally expensive. Usually you need many orbits, as you underline here, to do proper average of your torques and things. But over so many orbits, a disk that is subjected to the MRI will change its profile. It's very hard to do some clean work on this because you have a simultaneous evolution of your planets or your secondary and of your disk profiles. It's quite messy actually, and extremely expensive.
Yeah, no, you're right that here we need many orbits, and that's of course a drawback for more physics, including.
And then you open a Pandora box of what should be the beta of the gas, and so on and so forth. There are many other parameters that need to be taken into account.
Yeah. No, I think that, I mean, I see that really more as an interesting science project that, again, could involve a few people, as a subset of people that decide to do it. A small project inside the consortium or even outside the consortium. But it's really like a science project in itself. We haven't done anything like that, right? So, at least in the context of this study of decay of EMBH, so smaller black holes around bigger ones. Yeah. Because my understanding, Scott, I don't know, you can correct me, that the simulations that have been done now, which already been done with GRMHD, they normally do very few orbits, right? They normally look at the very last phase of the evolution of the binary.
Yeah, so that's true. We can only handle like tens to maybe 100. I would say tens, less than 100 orbits when we resolve the black hole on the grid, the black holes on the grid. And that's just the dynamic range issue. With this, if you excise the central cavity, then we can do hundreds of orbits. I'm working on finishing this paper that we're writing with a former intern, and she found that so after after 500 orbits, we get angular momentum equilibration. So meaning, you know, J dot is flat over radius, and so we can compare to long-term 2D viscous runs, and we get similar results, but the number of that we get in A dot over A is a little bit different. So so we think that things seem to kind of equilibrate a little bit faster with MHD than with viscous. But I mean, this also could be a function of the effective alpha that we have that the MRI yields at this aspect ratio. But anyway, we're getting there. We can do the CVD too. I think the number of orbits that is sufficient to compare to a relaxed CVD disc.
Okay.
Cool.
Okay. Well, that's interesting.
Yeah, I'd love to see that comparison.
Yeah.
You know, hope to have it out soon. So.
Okay. Yeah.
Should we define at all like the types of output we want, or is that just something pretty generic that we'll figure out?
So there are one thing is, you know, what type of
Or diagnostics, I mean.
what type of metrics, diagnostic metrics to do. Okay, so we did write something yesterday, but very crudely. Let's see. I'm looking for the place where we said analysis. Maybe not. So let's put it somewhere. Okay. Analysis. Okay, here. Input output data structure and format. Okay, yeah, we didn't say exactly what. So, right. So the focus we said we had in mind that should be on obviously measuring both the mean torque and the fluctuations of over the mean torque. So let's say.
Like outputting the torque with some frequency that's a function of the orbital time or something like that.
Yeah. So. Yeah, we have to decide also how frequent the outputs have to be dumped.
Yeah, so at least for the KITP code comparison, the frequency needs to be high because gravitational torques change pretty fast.
Mm-hmm.
So I think we are using 100th of binary orbit, if I'm not mistaken.
100 of orbits or 100 times per orbit?
100 times
100 per orbits, yes, sorry.
Yeah,
see, let's say 100 outputs per orbit. Yeah. Does it match more or less also what you've done in the?
Yeah, that sounds
similar.
Yeah.
Okay. Yeah. So the analysis. Of course, you know, it can be done in different ways, but I think it's easier to say that at the beginning, I mean, at least in the first phase of the comparison, we do post-processing. So we don't do, because on-the-fly analysis, again, depends on the type of code. So post-processing, everybody is capable of doing it. So I would say.
Yeah, I mean, personally, I wouldn't want to output 100 files per orbit, but that's just depends on where I'm storing my data.
Yeah, there is also this aspect, but
yeah,
I think the advantage,
in the code.
The advantage of post-processing, we can have a common script. We could have a common script, a common Python script to do the analysis, for example. I like the idea of having everything as uniform as possible in the analysis. Even the most obvious things that are kind of trivial, but
I'm not sure how common the script can be, because for example, if you had a script to calculate the torque with some density grid, you'd have to choose the coordinates. So maybe most people would have like polar geometry, but if not, then you might interpolate to match someone else's, and then you lose some information with every interpolation. I don't know how much one script could work for all codes.
Yeah.
If there's different grids and different grid geometry, things like that.
Yeah, but I mean, you can I mean, you can always convert the coordinates. You can decide that you're going to provide the outputs, using radial functions, for example, where radius can be defined to be the cylindrical radius, and then people have to measure that. Basically, they have to measure quantities, for example, as a function of cylindrical radius, and then how they get to cylindrical radius. And you're right, depends on what coordinate system they use.
So maybe it's fine.
Right. No, but you're right. I mean, in detail, there might be some slight differences. How are you doing this part in the KTP one, Alessia?
So actually, everybody is calculating its own quantities, like by itself. So we're not. I mean, there are common scripts, but I believe at least particle codes people are computing quantities as they see fit. So like for particles, basically. And then we uploaded the time series of, let's say, torques and eccentricity and momentum and whatever diagnostics. Sorry.
I just had an idea. I mean, maybe it's not worth the trouble, but I guess you could bless you. You could define, you make up a toy model file that's not an actual simulation file, and then everyone can test their script
inside
on it. Or, I don't know, just to make sure that there's not
that you get this,
subtle mistake.
Yeah, that could make sense actually.
Yeah, no, that's a good idea. So let's
that
call
could be
it
a task for someone.
Yeah,
Well,
let's call it analysis benchmark or something like that. Right? You want benchmark,
to test your scripts for calculating certain quantities. I don't know if we only look at torques or we end up looking at things like vorticity maps and stuff, right? There's so many options.
Okay.
So how far will we go?
And then, once that works for everyone, then people can do their own thing because they know
right, then they
the
can
same.
just do it with their own.
This is a good, that's a good approach. Let's say link some nice benchmark to verify close instances of difference. Consistency. Let's see how analysis different codes.
And I would suggest for the torques to also output torque from different regions. This could also just be done in post-processing, but to look at torque inside or outside of this hill sphere, for example, or inner or outer disk,
Different radial distances.
And that could be really helpful for diagnosing differences between the codes.
So from second, because it's
like from the inner boundary to the position of the, I don't know, that's more cutting it in half, but
it's also different distance from, close to the perturber. Or far from
or
the
farther
perturber.
away, so you could have different.
Starting more or less at the ear radius, right? Because people will have to resolve enough the ear radius to do this stuff. So H.
So you effectively exclude the material that is within the Hill sphere from the torque calculation, right?
This is a matter of discussion. I know that you would have brought this up. So I think we should try with both, right? With doing and not doing it.
Yeah, I feel like it's worth looking at, even if you would not consider it, to be included in reality. That's a different debate, but I think it still should be measured in the simulation.
Okay.
What's your take on that, Frederick?
Excuse me, I didn't hear you.
Yeah, what's your opinion about that? So you were asking it because you were thinking of not including the.
Yes, usually when you consider large mass planets embedded in disks, and with the ratio of the secondary to primary mass ratio you have here and the aspect ratios that you consider, you can say that they are analogous to large mass planets. Things which are surrounded by a circumplanetary disk. Then you exclude this disk from the torque calculation because in a way it belongs to the planet and it cannot affect its migration. It migrates with it. But its size it's not exactly the Hill radius. It's a fraction of the Hill radius. So from angular momentum conservation considerations, you can say that the maximum radius of the circumplanetary disk is 1/3 of the Hill radius at most. So maybe you would like to exclude a smaller fraction of the Hill radius, or we could exclude a variety of fractions and see how the torque depends on the fraction excluded.
Yes.
But to be clear, I don't think we should exclude any of the data. We should keep it all, and then we can compare with or without.
Yeah, I would tend to do that also because this thing also depends on the softening that people use, right? Smaller or larger softening would affect where to cut, right? Where to make the exclusion. So I would also have the approach that we keep everything, and then we can do the analysis in this way, looking at excluding, measuring the torque, and then doing it with it. But
I'm not convinced that it's not important, but maybe that's a different discussion. Because it's not that it's bound if it's flowing in and it's flowing out. And so if there's a preference for gas to flow in front of the black hole, for example, versus behind, there's a persistent asymmetry. So it's not the same as like a moon, for example. But
Alessia I think she had a comment. Alessia, do you have a comment on this?
No, I actually wanted to suggest another type of thing to look at, but probably it's better for the, let's say, second part of this comparison since it involves the gap opening.
Yes, right. So this setup now is without, but yes, yesterday we said maybe we could have another, well, if we erase the Q, of course, then we will go into a regime where you would maybe open the gap, depending on alpha, of course. Alpha is large here.
I think even with these parameters, you would have some change in the density profile though. So did you have a suggestion for what to compare, like the shape of the gap or something like that?
One thing that I would be interested in looking at is the eccentricity of the circumprimary disk, since it opens a gap, the planet opens a gap and then there is a disk around the primary, just out of curiosity, if that's eccentric, that it gets eccentric or not.
You mean the eccentricity like of the inner disk inside
yes.
of the gap? Oh.
Yes.
Mm-hmm. Interesting.
Just because it's, I mean, I don't know, we had some discussion with Jonathan at KITP, and it seems that if you start with like a disk around the primary and then a secondary without circumbinary disk, then if the disk around the primary feels the 3-to-1 resonance, then it gets eccentric. But if you have the circumbinary disk, which is feeding material, that doesn't happen. And it stays circular, but it's still something that I don't think many people have looked at. But as I said, it's something possibly like a step 2 in the project.
Yeah. Mm-hmm. Yeah. So. Okay. Right. So, I mean, of course, this Google Doc, we can update it until the next meeting. I will try to contact everyone to decide when this meeting could be. Realistically, at least for me, it's impossible to do before September because, like many of us, I think there's many conferences and travel. So I would target for September to really finalize all the remaining things and have a clear group of code captains and one analysis captain, one who gathers in the meantime, I will reach out to some people who could not make it to this meeting online or in person, so that by the time we do the Zoom, everything should be almost completely set. We just have to agree. But,
And then what the Zoom is just for,
the Zoom is to say agree finally on, okay, now we really write down the initial conditions, basically. Well, it's almost written, but there are always a few things that have to be finalized. And someone says, okay, now I will take care of distributing, I don't know. Well, we can do it in more than one way. We could have, so at KTP, what did you do? You had someone who distributed the initial condition, meaning gave the profile and all the other
Yes.
parameters.
Yeah, that someone was Paul. And I think
That's
Paul
the
and
same
then
person,
Paul and then put together the overleaf where they put like all the common initial conditions and the description of the diagnostics.
Right, yeah, so this person ideally would be also the one who gathers the analysis or oversees the analysis. I guess that's what Paul is also doing.
Yes, exactly, yeah. And now Paul is just, is so patient to analyze all the data that we uploaded.
Yeah, so this, of course, it will be hard to find someone who wants to take over this time-consuming thing.
well, it could be that you request, people parse through their own data and send it in a requested format.
Yeah.
It's much more simple
Yes.
for someone
You
else
don't-
to then compile.
Yes, you don't need to do all the work. Yeah,
Yeah.
that's yeah. Actually, in
Also maybe, sorry.
yeah, go ahead.
Also maybe if people are interested in joining the project, but are not like experts enough to run simulations themselves, then they can contribute to the analysis, because at the end of the day, we have HCF5 files, which you can open without even knowing what it is. So.
Yes, and actually, this is something that, if in the next couple of months, we don't have a forecast, let's call it like this, or who could be this person or these persons, we can also make a call inside the consortium. For example, recently, something like that has been done by one of the work packages that needs some expertise for something. And Alberto Cesana, he basically, you probably saw his email, so he's calling for some expertise, essentially. So this is something that, we could call for help on the analysis in the same way.
Yeah.
Yes. Clarifying again, okay, if you're not a code expert, don't worry, because you could help a lot with the analysis. And so we could reach out like this as well. Yeah, so let's see. Okay, so let's say I put analysis content. And it could also be the initial condition. Also be ICs. Okay. Yeah, and then in terms of the structure of how to communicate, we could do something similar to what they're doing for the KTP one. Yeah, we could have an overleaf and a Slack channel. I'm not super fond of Slack in general, but
Because you have 5 million channels.
Yeah.
and then I don't look at everyone. That's basically. But yeah, but I like this thing about starting the overlay pretty early in the project. This I like, because then you can put plots and you see things that they're there, right? It's like a book, basically. You go and look at that. Yeah. So let's say start.
You can just copy this Google Doc into an overlay.
Yes, exactly. That would be the first action item.
Action item right now, I think.
Action item.
Can we
is
get
you
overlay
start.
captain?
Exactly. Also that I can do. Right?
It's really taken over the world. Isn't it?
Oh, yeah.
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 I almost forgot what it's like to just do it on my own.
Yeah.
computer.
Yeah. Awesome. Good shot.
There is still a problem that you always need to be connected to the internet.
I agree.
I think that's, and then when you push your through Git, your changes is complex. But
trying to scope that is he left. Okay. Yeah. So I guess, I mean, unless if there are no other urgent points, we can just move to the next step, the next meeting. I'll take care of that and I'll reach out to other people in the meantime. Frederic, you had some last point to make, or?
No, I'm fine with what has been said. Okay.
Actually, I wanted to reply. I sent a message I sent to you was actually directed to Scott, but it works in any case. Okay, okay, and yeah, so yeah, we are going to finish a bit earlier the call because myself and others have to run to the airport basically. But I mean, if there is some other important point, we can go on for another couple of minutes. Okay, so if not, I guess we can call it a done deal.
Shall we end the stream and stop the recording?
I think so. Yeah, because at this point, I guess we don't go on with other things.
Everyone okay with that online?
well, they have no choice.
Not that, yeah, not that you have to address it.
Who continue to be in their own Zoom.
Oh, there you're right.
Yeah.
Okay.
So,
Thanks, everyone, then, and talk to you soon over email and the next Zoom meeting.
Thank you, everyone.